Ladies and gentlemen, the topic of my presentation is Industry 4.0 from the perspective of applied research. And I think the most of all of you know Industry 4.0, Internet of Things or smart factories are only possible by interactions of different disciplines. For example, production engineers, ICT technology, information and communication technology, respectively, electrical engineers and others. I have subdivided the presentation here in some facts, at first some facts and figures about Fraunhofer, then Industry 4.0 as industrial transformation, and the main topic is requirements for data-driven production, and on the end some examples of applied research results in Fraunhofer for solutions in Industry 4.0. At first, some words about Fraunhofer. Mr. Jasper Neide explained something about his own institute, and here you can see we have a total revenue in the last year of 2.1 billion euros in 2015, and a special fact in Fraunhofer in comparison to Max Planck Association, Helmholtz or Leibniz Association in Germany is we have infrastructural expenditures and defense research, and in the so-called contract research we have less than 30% as space funding, and 70% we have to acquire in competitively from industry and publicly financed research programs. A lot of colleagues from other countries come to Germany and ask us, what is the key of the German innovation system and what is the key for the success of Fraunhofer? My opinion is the most important aspect is this financing mix. The must to go to the industry and to create projects as basic for the financing of the institutes. And you can see we have at the present time 24,000 people at 67 institutes for innovation in products and in processes. Both is in our focus. And the next slide shows the 67 institutes in Germany are distributed on more than 100 locations in Germany. And in international area you can see here our activities worldwide. In Europe we are the largest research organization for applied research. And what are our major goals for international cooperation? The first is to learn from the best in the world scientific community, and the second one is to support the German and European industries in foreign markets. Therefore, we have currently 7 independent subsidiaries in United States. This orange-colored locations in United States, in Chile. In United States we have 7 legal institutes. In Chile, in United Kingdom, Italy, Austria, Sweden and Portugal. And every institute abroad have a strong link to a partner institute here in Germany. The international revenues in 2015 was 291 million euros, and 2/3 we realized in Europe and 1/3, nearly 100 million, in the rest of the world, mostly together with the industry. The international share of our total research contract revenue is, from the total revenue of Fraunhofer, 25%, with tendency to rise in the project, also in the contract research. Our research covers future challenges, as you can recognize here: health and environment, safety and security, mobility and transport, communication and knowledge, energy and raw materials, production and services. And the next chart, focusing on the topic Industry 4.0, you can see this crosses all our research fields, because Industry 4.0, what I mentioned at the beginning of my presentation, is highly multidisciplinary. Examples here are human-machine interaction, cyber-physical systems, especially in manufacturing, data security, low-latency communication. Here in Berlin, we work very strong about low-latency solutions, and cognitive algorithms. Energy self-sufficiency in autonomous cars or production facilities, decentralized multi-agent logistics, and overall resilient systems in the physical and in the cyber world. Also in the European level, I'm also a member in different European working groups in Brussels. Is the main topic today, resilience in physical and in the cyber world. These are technological solutions on the way altogether to Industry 4.0. But in the next topic, I will take a look to the frame conditions for this industrial transformation. In general, the general frame conditions for industrial transformation are socio-economic and technological drivers, political framework, for example in Germany here, merging of physical and the cyber world. And second, the dimensions of Industry 4.0 on enterprise level are management level, ICT infrastructure level, and production level. In these three levels we subdivide our activities, but we need a solution merged of all the levels together. The socio-economic framework is changing in terms of new innovation players, for example China, India, South Asia, and Africa. For example, the strong investment of China in Africa, in African countries. Demographic change, aging and declining population in Europe and in North America. We get more, we get fewer and older workers. On the other hand, growing population in India, Africa, and Asia. And for both we need different solutions. Changing consumption, sustainability, customization, sharing economy are topics which we have to consider in this field. Together with the achievements in mainly IC technology, this leads to new products, new process, and we should not forget new markets. We work not only in our innovations in optimizing of processes of products, we need disruptive innovations for new markets. We have in Germany a national platform for Industry 4.0. 4.0 is very well organized, and the question was, how can the government support this industrial transformation in a good way? In the case of Industry 4.0, we have a national platform headed by the Ministries of Research and Economic was installed in Germany. We have different national platforms, for example, for electromobility, for energy, renewable energies, and we have also a platform now for Industry 4.0. And in the platform you can recognize in the chart work together leading top management, leading persons from the industry, from the policy, and from research and development. Fraunhofer is very active in this national platform. You can see in the box in the middle, Professor Bauernhansel is a colleague of Professor Jasper Neite from our institute IPA in Stuttgart, and some other colleagues from Dortmund, from Berlin are very active, from Bonn in IT technology in this national platform. Industry 4.0 is about merger and collaboration between digital, cyber and physical world. As I mentioned, every hardware has now a digital shadow represented by software. And this is, I'm a mechanical engineer, I come from production technologies. This is a total new culture also in the work of the engineers in the production world. Every hardware has a digital shadow for products and also for the processes. On the left side we have the possibility using software to cooperate easily in business and social communities and to link different data efficiency. And on the right you can see on the right side we have the hardware with the function enabling machines to act adaptive, intuitive and robust, as well as storing, distributing and analyzing data. Those together leads to cooperation productivity of humans and machine. It's a great topic. Also what Professor Jasper Neite mentioned, my membership in the board for the National High-Tech Strategy in Germany. We have to consider not only the technological development, also the participation of innovations in the society is a very, very, for example, for such technologies, human and machine interaction. What does this picture mean here? We have in the Fraunhofer headquarters defined a special layer model for Industry 4.0, and you can see here the business layer. The business layer is depending on the industrial sector. New structures of industrial and business organization become necessary concerning business models, management issues, and human resources, for example, education and training. And the second layer is the ICT layer. This is the key enabler for Industry 4.0 and data-driven production with the components of standardization, data rates and low latency communication, data security. I will give in the next chapter a little bit more, a deeper insight to this point. And the core of the layer model you can see here. This is characterized by cyber-physical systems, connected machines, machine learning processes within machines, and systems for process automation, and autonomous systems, sensors, and sensor fusion. Autonomous systems, for autonomous systems, we work in Germany coordinated in the national level about autonomous systems for production technologies, autonomous systems in the medicine sector, and also in the field of logistics for transport and automotive industry. And in all these fields we have the same technological basic. In Germany, you can see on this chart, we look that we get 400,030 new jobs, and at the same, and on the other hand, we will get an elimination of 490,000 low-skilled jobs in the future. For example, classic assembly activities. These numbers come from a study from Fraunhofer, together with an industrial association here in Germany. And on the other hand, you can see it, Industry 4.0 will likely lead to GDP growth of about 30 billion euro and requires investments of about 250 billion euros. And here, a look at the international level. The economic potential of Internet of Things, IoT, is estimated to be in the range of 4 to 11 trillion US dollars in 2025. And we have here the 9 areas with the highest potential. Of course, factories, cities. We have projects in the Fraunhofer Association, the factory of the future, the city of the future, and also human work and well-being, retail, logistics, work sites. You can see it faster than I can mention this. And here a special view to activities. We have also colleagues here from United States. We have strong cooperation with partners in United States. What has happened in United States versus in Germany? I myself have had discussions, for example, with Penny Pritzker, Secretary for Economics in United States. What can we do together? What are the actual position? And in general, in our eyes, is the situation today. Germany is leading in technologies related to machinery and engineering, microelectronics, embedded systems, and also sensors. We are a country of sensors and actors in Germany, and automotive application and chemical processes technology. And United States is today leading in clearly in software-related technologies and services, software development, data analysis, IT service, networks, servers, clouds, business intelligence. And the result is we in Germany focus on the implementation of ICT into machines. That's the background for generating Industry 4.0, and while in USA attach machines to ICT in the frame of the Internet of Things. Good precondition for more cooperation. And here a little bit in comparison of the situation in our eyes, from our point, between Germany, United States, United Kingdom, it's a little bit similar, and East Asia. And first some words about Germany. In Germany, we have the precondition we have had in the last years no deindustrialization effects. We have a strong industry, but we are a little bit late in digitization. Smart industries, Industry 4.0, and customized production are topics in our research and in the development in the companies. And I think for the future, I feel it in the discussions on the political level. We have another approach. We have an approach, and this approach is an advantage. Our human-centered approach for production processes. In our eyes, it is a task for us that we bring people in the production processes, but for the right activities. Not so, our optimization processes have not in the focus to bring the people out of the process. In comparison, United States and United Kingdom, in United States especially, we have a strong in software and ICT service, what I mentioned by the other slide, but we have also had in the last years in some branches a deindustrialization, for especially in United Kingdom, and now there are strong activities for reindustrialization, and ICT is still in focus. And what we have learned in different conferences, in discussions with our partners in these countries, is a little bit less human-centered, the development of production processes. And in East Asia, with a high interest in low-cost manufacturing. You can remember the low-cost car in India and other developments. We have, in general, an aging society. We have declining workforce and higher, step by step, also higher salaries, income revenues of the co-workers. And we can recognize the use of robotics and full automation to cut the production costs in the future. That's our view to the global market in new production technologies and what have we to change by Industry 4.0. After talking about the frame conditions, the potentials and challenges for Industry 4.0, I want to focus on the 4 essential requirements for data-driven production. This was, in my former slide with the layers, the second one, the IT level. These 4 essential requirements are standardization, data security and safety, data rate and low latency communication, and machine learning, very important aspect. This is a little bit a difficult chart, but it's very important to understand the different functionalities in Industry 4.0. The different system levels requires different preconditions. Let us start by the lowest level. In the physical level, the embedded systems, the real production systems, with actors, sensors, systems, connected controls, is the definition of standards very essential for compatibility and system interaction. In this area, we have had in the last year a great step forward. We have made a great step forward. In the second level, the networking level, this means this level, basic data service, information fusion, smart data service. In the networking level, between all the communication partners, we need first data security for a trustful data exchange. Only when you can guarantee data security, for example, small and medium companies, enterprises, take part in data exchange. Her capital, its capital, the capital of these enterprises are the IP, and the IP is in the data represented. In the networking level, between all the communication partners, what I mentioned, we have this data security, but on the other hand, we need also machine learning. When we have in an enterprise or in a production system 10 or 100 times more communication partners, we need machine learning for automatic programming of the controls and all the computers which are in different devices in the production system. And on the other hand, the machine learning process leads also machine learning process for the automation of the programming processes in this level, but in the enterprise level. And we have made a very, very interesting experience. Machine learning processes, big data analysis, bring us to new markets and new products, not only optimizing processes like in a branch. In the next chart I will give a little bit deeper inside, also total new markets and total new products. Some words to, I know a lot of colleagues in your community work in this area, but some words also about our reference architecture model for Industrie 4.0. It was defined by German organizations Bitkom, VDMA, the mechanical engineering organization, and ZVEI is the electronic organization of the German industry, together with the national platform Industrie 4.0. And the model is characterized, if you can recognize, by 3 dimensions. At first, the production life cycle, subdivided in type and instance. Secondly, in functionalities according to standard series. And the third dimension is the digital reproduction in 7 layers. The hierarchy levels were in comparison to the EIC completed with product level and the connected world. So it means here in different functionalities, the new was the extension to product and connecting world, new functionalities in this area. This chart is very important to understand when have we a chance to realize disruptive innovations, and when will we get as a result of our work evolutionary innovations. When we use methods or solutions for Industry 4.0 in a branch to optimize the processes, for example, in the automotive production. We have a lot of projects with the German automotive industry and also in other countries. In the most cases, we get optimized processes and optimized products, but we have the same market and the same type of a product. When we have by deep learning or machine learning, deep learning, and data analysis cross to the branches, different data, then we have the chance to get disruptive innovation with new products or new processes, and on the end, what is the best of all, with new markets. And here, for this data exchange, in the vertical space or in the horizontal space, we need in every time data security, and for this we have in the Fraunhofer Association with nearly 10 institutes created the industrial data space. Now the industrial data space is on a European level, and the industrial database, you can see here the main components, and the most important characteristic of the industrial data space is for the customer. We have we have no the existence of a central cloud with a single owner. The data sovereignty of all the participants is realized by the use of single servers by all the participants who determine the own data availability within their own cloud. Sorry. The central software component for the data exchange between the different participants is the industrial data space connector, which is actually implemented as two components. At first, an external industrial data space connector facilitates the exchange of data between the participants in the IDS, and secondly, the internal industrial data space connector it is very similar to the external, but is typically operated, protected within a certain enterprise. Additional to, as you can see here, additional to the connector, we have a broker as a software component. The broker has the responsibility for the functions clearing, index, registry, and yellow pages. And another complementary component on the right, upper part, you can see, is an app store for special functions for enterprises. How is the actual situation? You can see we have founded and registered in January 2016 an association. The association is a backbone for the industrial data space, and over 30 members from industry, research and development in industrial association from 7 countries work together. 80 partners are ante portas or have the wish to cooperate. We have, I think, more than 200 use cases in operation, and this association pools the requirements of the industrial data space from the different branches. And as you can see, we have automotive industry, Volkswagen. This is a special automotive industry like Volkswagen. We have Atos from France, is a part of Siemens. We have small and medium companies like SICK. SICK is a producer of sensors and actors. Comsa is a communication company. Of course, Fraunhofer, Bosch, for example, Boehringer or Bayer chemical industry, Boehringer pharma industry, and all together use her data in this, merge her data in this secure data, industrial data space. Other point, the first was standardization by the frame architecture. Second point was data security, realized by the industrial data space. Third point, low latency. I think your organization, everybody knows the problematic of latency, and to achieve digitized and network production, as you know, we need extreme low latency for real-time activities, mobile and broadband communication towards the range of 1 millisecond. And because 1 millisecond is our fast reaction of our senses, and this is the background that we call an internet, which have in as longest tactile, as longest latency, 1 millisecond, then we speak from a tactile internet. This is the background. And the advancement of 5G in next generation via technology for the tactile internet is also in strong research activities, especially here in our Fraunhofer Institute, Heinrich Hertz Institute and Focus Institute here in Berlin, together also on European level with other partners. Why is this, the latency very important? it enables the applications like industrial internet, real-time machine communication, autonomous transport and logistic systems, or also, for example, in hospitals by supporting medicine activities. The assistance technologies like real-time in telemedicine, I mentioned this, and augmented reality. And very interesting, our institute Focus here in Berlin measured the latency because they want to use information from the cloud for a control cycle in a real machine system here. And the exchange, the data exchange via internet between Berlin and Dublin was nearly 20 milliseconds. Between Berlin and Bordeaux, the double, 40 milliseconds. And between Berlin and Boston, they measured 80 milliseconds. It's, in my eyes, a very nice example. We need, in my research field, for example, high-speed machining, less than 1 millisecond. When we want to use in control algorithms data from the server and the background which we have by data analysis. That's a challenge. In order to achieve the necessary latency and data transmission rates, we have, what I mentioned, a lot of activities, and the technology for fast communication is here and is there. The technologies are there, but we have constantly to improving, and we work about a 5G internet test bed here in Berlin. In Berlin we are on the edge in this field, and with Focus and Fraunhofer Focus and HAI, also Heinrich Hertz Institute, that means Heinrich Hertz Institute, and latency needs to be reduced by 10 to 20 times, as I mentioned. Data rates need to be increased, you can see it on the left, by a factor of 12, and our approach is subdivided. Our solution approach, you can see on the right, is subdivided the system in a so-called rainforest approach, so providing coverage level, hotspot performance level, and device to device communication level. Big data is a huge amount of different types of raw data. Out of this pool we can generate smart data. You can see here the different steps by asking the right questions, and we obtain specific information. This information enables to build up knowledge to make the right decisions for a machine or for a human. This ends up in higher productivity and therefore an added value creation in Industry 4.0, healthcare, logistics, or also other applications. And now some words about deep learning. A new generation of artificial intelligence-based machines, the so-called cognitive machines, is about to enter our everyday lives. I think that most of you have also experiences in this field. And flexibility and versatility can work in different settings and on various tasks without reprogramming. Interactivity, for example, ability to communicate with humans, or iterativity and memory, can memorize learned things and search strategically to find answers to new questions. Contextually and adaptability can understand the given context and react accordingly and adapt to new environments. Today in the afternoon, when I go from the conference, we have a very important event with a lot of Fraunhofer Institute's leaders about our strategy and our next steps in machine learning. We have an official information we have in cooperation with the Max Planck Association for the development of new algorithms of deep learning. On one hand, we have as research organizations for applied research to look for applications of machine learning, and on the other hand, we will also go strong steps ahead in development new algorithms. So what is the work looking like at Fraunhofer to face the challenge to make evolutionary steps? And in the following I will present some selected research projects starting with focus on process and connectivity, 4 charts, 4 examples, followed by deep learning in manufacturing, in ending and application, and smart logistics and human integration. At first, processes and connectivity. My own research field when I was the institute's leader was forming technologies and machining, machine tools, development of machine tools and controls. And in the future we speak about and we develop cyber-physical systems, and we combine computation with physical processes, but automation software still needs to be changed manually. Next generation intelligent modules, machine tools and parts can configure themselves when attached to the machine. Yesterday I was in a board meeting from a German machine tool company in the near of Lemgo. The location of the institute was in Bielefeld, and this company changed their product portfolio from conventional machine tools to cyber-physical systems. It was very interesting. Also a change of the staff. So all the engineers change with IT specialists and so on. And machine learning, the next chart. Machine learning can be used in various ways for optimization production processes. And one example also from my own research field you can see here is the prediction of material conditions during forming processes and the according adjustment of machinery. From today, the so-called process window for a reliable forming process without wrinkles in a car body part or tears in such a workpiece are only based on constitutive laws and simulation. Very difficult process with high efforts in simulation, and in the future from sensor measurement at selected points, machine learning algorithms can be used to predict the whole material stress distribution associated with different forces activated by the actuators to select the optimum setting in the process. It's a very, very nice example where we change from the process design based on constitution laws to based on sensor data and the analysis of this data. And the third example is from our institute for material flow and logistics in Dortmund. And in this case we have a smart, networked and autonomous swarm logistic approach. And maybe you can recognize in this ball, in the middle of this ball is a small drone. And the drone is a transporter. It's a transporter for a workpiece, for different packages. And this is the solution is based on swarm robotics, advanced ant colony optimization algorithms. And we have a combining of rolling process and flying process. Rolling and flying technology often is used for optimal safety and efficiency. And the system only flies when necessary. And in this case we can save energy and the recharge of the batteries is realized up and descending from the high racks from the spiral device and continue. So, and on this spiral you can, here we have conducting functionality in these rails. Is realized in the industry. We was on the Hannover Fair with the solution, and now comes the first logistic enterprises and use this approach. I think some.
And are you have any questions?
All things are clear. We have to do.
Maybe I can start with one question from my side. This industrial data space is a very important activity, and you told us that it is one of the prerequisites to enable new data exchange between companies. I'm missing on your slide large players in this area like Amazon, like IBM. Is it this activity and let's say a competition to the commercial cloud platforms, or is it more or less a complementary activity?
It's a very interesting question. When we started with the activities on the table. When we started, was my opinion, at first, we need a discussion about the relevance. Have we to start with such an activity in industrial data space for security data exchange? And we would get an answer from the industry. And the answer from the user industry, which use data space, but have other business, automotive industry, chemical industry, pharma industry, assurance, all of them told us we want to start with Fraunhofer as a neutral partner. We have had also in our roundtable companies like Telecom, SAP, or others, also from the communication industry, and they was careful. They were careful. They want to have this business, and now for this business, the Anwenderindustrie, the application industry, have their own association, and the driver for this way was the trust to a neutral partner like Fraunhofer. We have not a commercial interest.
Maybe a further question also related to this issue. You see a lot of young, very inspired people here. Is this IDS also let's say, an open platform where young people, entrepreneurs can create their own apps to create new business models, or is it a closed shop?
Of course, it's open, and Professor Jasperneide can be the door to this room. Your colleague, Professor Otto, is the leader of this project, and if you call him, that we have partners here, I think everybody is welcome for cooperation. Maybe on the end there is a decision, is this an add-on for the functionalities which we have, or is this a redundant new partner?
Okay, so again the question to the audience. No question?
I have a question about the Industry 4.0, and because you were around the world with the institutes and so on, so my question is how recognizable is this term around the world, and can you say that you work with the Industry 4.0 in Chile, in China, and so on, or how this term and all the technologies that are included fits to the markets around the world?
In our activities, we work together, for example, with the colleagues in China, and there was a wish from the Chinese government, for example, to use also our standards and to take part also in the industrial data space. When we can realize this is not only a German solution or a European solution, is it open worldwide. And we have, on the other hand, also activities in the other countries. And we look to compare and to cooperate in these ways. But we are open for all the different areas worldwide. Was this a question?